everything we'll go through today. Okay, so today's topic is Pell equation infinite descent. It's really about more applying infinite descent in Pell equation to some Olympiad problems. And you'll see how quite powerful it is in the rather unrelated seeming problems that we're going to do today. But let's first of all start with some preliminaries. Get writing here. Okay. First of all, let's define our terms and be sure that we're clear on everything. What is the Pell equation? A Pell equation is an equation of this form: x squared minus dy squared equals 1. And this in itself is the most basic form of Pell equation, where if d is a perfect square here, is a perfect square, then the left-hand side is just a difference of squares, and you can factor this into x minus dy, x plus dy equals 1. So it's not so interesting in that case. But when d is not a perfect square, so this is difference of squares. But when d is not a perfect square, it gets a lot more interesting. And it turns out that there are an infinite number of solutions when d is not a perfect square. There are multiple ways to derive and compute these solutions. We won't go through all of them. We'll just talk about the way of doing this in infinite descent. And one more thing before we get to infinite descent is you might wonder, what if that constant, is that constant 1 on the right-hand side really important? What if it's not there? If you replace 1 with any other constant, it may or may not have a solution. In some cases, it will have no solutions at all, but in other cases, it will have an infinite number of solutions. But yes, today we will be analyzing, in our problems, we'll have a more general form of this Pell equation, where 1 is replaced with a constant n, and n could be positive or negative, or really anything. Okay, so that's what a Pell equation is. What is infinite descent? Infinite descent is a method of solving Diophantine equations. Diophantine equations being just equations where we solve over integers or positive integers. And the idea of infinite descent is, suppose we have, let's write p, okay, so p of xy equals 0 is some Diophantine equation, is a Diophantine equation. Then what infinite descent is that if we have a solution, x, let's say x, x1 comma y1 is a solution, then the idea is that when infinite descent can be applied, the idea is that from this solution we can generate a smaller solution, x0 comma y0, where you want this to be smaller than x1 y1 for a certain definition of smaller. So smaller could mean so smaller here could mean any kind of well-defined smaller. So it could mean x0 is less than x1, y0 is less than y1, or even x0 plus x, well, y0 is less than x1 plus y1. You just need the ordered pairs, all ordered pairs to be well ordered. So you can compare a solution to another solution and say, yes, this is smaller. And here the idea is, if we're working over positive integers, so over what we'll denote as n squared, this means all ordered pairs of positive integers. If we can keep generating a smaller solution, then at some point this has to stop. So there has to be a smaller solution. So either this means of generating a smaller solution just comes to a dead end, or we get a contradiction, and hence we show that there's no such solution. So let me just write this. Over n squared, this process must terminate, or else we have no solution. Okay. Those are our basics. Now, just to get an idea of how one of the means of solving Pell equations, okay, which we can actually do by infinite descent. And the key to doing that is an identity called Brahmagupta's identity. So Brahmagupta states that this identity is the very convenient following: x1 squared minus ny1 squared. So note the left-hand side form of our Pell equation, times x2 squared minus ny2 squared equals x1 equals x1 x2 plus n y1 y2 squared minus n times x1 y2 plus x2 y1 squared. So now note how we're taking, if we have applying Brahmagupta's, that means if we have two solutions, x1 y1 and x2 y2, then we can generate a solution to our Pell equation by the solution being given by x1 x2 plus n y1 y2 comma x1 y2 x2 plus x2 y2 plus x2 y1, because note on both on the left hand side it's product of something squared minus n times something squared, and the right hand side is something squared minus n times something squared. Okay, this is very neat. Note, by the way, that this identity is algebraically true. So you can take this over not just integers, but also rational numbers if need be. And we'll actually see how, we'll actually use the domain of rational numbers today. But note that this is just, it's an algebraic identity. It holds for all x1, y1, x2, y2, and n. What this also allows us, what Brahmagupta's also allows us, is if we have, over here we're looking at solutions to the proper Pell equation, this Pell equation, x squared minus 3y squared equals 1. And of course it works because then this first term here is 1, the second term is 1, and right hand side is 1. What about general solutions, general Pell equations? If we have, so let's say now instead we have x1 y1 satisfies x1 squared minus n y1 squared equals k, and now we want to generate another solution to the same Pell equation where something squared minus n times something squared still equals the same constant k. Then to use Brahmagupta's, in order to get k on the right hand side, we'll need the second term to equal 1. So we'll need x to generate using Brahmagupta's to generate an infinite number of solutions. We'll need x2 squared minus n times y2 squared equals 1. Then if you apply the same x1 x2 plus n y1 y2, x1 y2 plus x2 y1, we'll get another solution to x1 squared minus n1 squared and y1 squared equals k. Okay. So actually, this actually gets us, really what it gets us is infinite ascent. where we go from one smaller solution and we generate an infinite number of larger solutions. Because you'll note that these, as long as we pick x2 and y2 to be positive, which of course we can do, take the absolute values, then then this solution will be strictly larger than x1, y1. As for infinite descent, you can apply the same thing in reverse. So you can say, if we have a solution, if we have a solution x1, y1, then we can solve for a solution xy that satisfies. So let me be specific here. So let x1, y1 be a solution to our Pell equation, general Pell equation, and x squared minus ny squared equals k. And instead of getting a larger solution now, let's get a smaller solution. So where we also have, so let's also use the same x2, y2, which is the solution to the proper Pell equation that will help us apply Brahmagupta's. So now instead, we can actually apply Brahmagupta's in reverse, by which I mean, let's get something, let's find an xy such that x times x2 plus n y2 equals x1, and xy2 plus that would be x2y equals y1. So as you solve for a solution xy to this system of linear equations, if we have an integer solution xy, then this xy should satisfy our general Pell equation, x squared minus ny squared equals k. And of course, we know that whatever solution there is to this system has got to be rational. X and y must both be rational. It's not immediately clear though that x, y are both integers, and we can actually see why x and y are both integers. If you look at the discriminant, if you apply Cramer's rule, look at the discriminant of the system of equations, then the discriminant is, sorry, not the discriminant, the determinant is that would be x2 squared here minus n times y2 squared. So I believe this is determinant. Okay, so determinant equals x2 squared minus n y2 squared, which equals 1 by our construction of x2 and y2. So this actually means that if you apply Brahmagupta's in reverse, you'll always get an integer solution. Final note before we move on to actually applying Brahmagupta's in infinite descent to Pell equation type problems. It's that so looking back to our general Pell equation, x squared minus dy squared equals n. So I said for some values of n, we're not going to have a solution to this equation. And briefly, to explain why it would be, if you take this, do we have another color? It's okay. For certain n, we're not going to have a solution, because if you take this equation mod d, then it follows that x squared is congruent to n mod d. And if you know a bit about quadratic reciprocity, this means that for half, or really it depends on d, but some residues mod d are going to be congruent to a square mod d, and some are not. So this requires n to be congruent to a perfect squared mod d. But if n is congruent to perfect squared mod d, then we I can't say that I can't be certain that at least as far as I know, I can't be certain that there always will be a solution. But certainly there should be a solution at least sometimes. If you just plug in a random x and y, that will give you a random n, and consequently that n has a solution in x, y. So going back to infinite descent here, as we talked about with infinite descent, either this process must terminate, or if it can always generate a smaller solution, then it's a contradiction. There are no solutions. So this process must actually terminate. And why is that? We'll actually see this more clearly in the problems we'll do, so I won't be too detailed here. But basically, it is that when you generate a smaller solution, sometimes the smaller solution might go into the negatives. And when you go into the negatives, you don't actually really get a smaller solution. So you want to be careful there. See, when is it that when you apply Brahmagupta's in reverse, your smaller solution is actually going to be negative, or in a case that it is negative, actually negative with larger absolute values. So long story short, basically, Brahmagupta's does terminate in the end, which we'll see. Okay. So now let's actually apply this to some problems. So the first problem actually we're going to do is IMO shortlist 2016 N5, which means it's so just the rule of thumb, N5 means it's about an IMO 2 to IMO 3 level in difficulty. But actually we'll see applying what we just talked about just now, it will actually turn out to be, hopefully it will turn out to be rather straightforward. So let a be a positive integer, fix a is a positive integer, let it not be a perfect square. What's the problem with it being a perfect square? Well, if a is a perfect square, then x equals 0 is the solution. Well, okay, we'll see. Anyway, consider the equation k equals x squared minus a over x squared minus y squared. So first we have the set of positive integers k, which admits a solution with a large value of x. And then b is, we also have the set of integers k, which admits a solution with a small value of x. And now we want to show that whenever, so basically, whenever k, for whatever value of k that has a large solution xy, we're also going to get a small solution xy. So essentially here, k and a are both going to be fixed. And so this is just an equation in terms of x and y. So what does this actually look like in terms of x and y? If we actually do the most crude thing and just expand this out, what we actually get is, expand this out, we'll get k minus 1 x squared minus k y squared equals negative a. Okay, so already this looks a lot like our Pell equation, but we have coefficients with for both x squared and y squared. If you look back at our Brahmagupta's, which we aim to apply, why do we want to apply Brahmagupta's first of all? Why do we want to do infinite descent? It's because we want to do a I should not say bijection, but we should say basically, if we have a solution xy, we want to be able to generate a larger solution, let's call it x prime, y prime, and also vice versa. So if we can actually do this, where large, I mean x is greater than square root a, and by small, I mean x is less than square root a. If a small solution can always generate a larger solution, and a large solution can always generate a smaller solution, a small solution, then we've showed, then the problem follows. So that's why we want to apply Brahmagupta's. But looking back at Brahmagupta's, this identity requires the coefficient of x, or coefficient of one of them, to be 1. You won't get an algebraic identity with a coefficient not equal to 1. So somehow we have to get a coefficient of 1. And that's our first trouble here. How do we get a coefficient of 1? Well, let's look back and remember I said here that n does not have to be an integer. It literally can be anything a rational would do. So to turn this into something that we can use Brahms-Gupta's on, let's just divide out k minus 1. Generally, when you're doing Diophantine equations, you don't really like to change the coefficients or constants into rational numbers, because oftentimes you'll have many more solutions in rational numbers than integers. But we'll be fine here. So it turns out we'll be okay. Anyway, okay. Sorry. Okay, I'll remove my keyboard. I don't need my keyboard. What's going on? Okay. Let's turn this to x squared minus k minus 1 times y squared equals negative a over k minus 1. Okay, so let's I'll copy over Brahms-Gupta's. Now I actually need my keyboard back for ease of reference. Let's put this back, copy this over there. Certainly if you guys take notes, this you'll have it in front of you, but we'll put this in front nonetheless. No, how do we copy? I don't think we can paste an image. Okay, well, that's okay. Oh, there we go. Figured it. Oops. And can we copy? Well, let's do it this way then. Okay. No, it's okay. We don't need to. All right. Okay, let's get going. So if you remember how we applied Brahms-Gupta's, that is, we wanted to find a solution to this Pell equation, but with 1 on the right-hand side. So we want something x squared minus k over k minus 1 y squared equals 1. So we'll need a solution. Let's see if we can actually just find a solution to this equation. If there's just a fixed solution, then that will be handy. So is there a fixed solution to this? Well, we can hope, because since we're just trying to find a solution, not all solutions, we can just assume that k minus 1 divides y. That way, this term will certainly be an integer. So exploring to see if we have a solution. Let's write this instead as y equals k minus 1 times y prime. So this becomes x squared minus k times k minus 1. Okay. K times k minus 1, y prime squared equals 1. And now the solution becomes quite clear. The solution would be y prime equals 2 and x equals 2k minus 1. Okay, so we found what we need. Let's just move this up here. Our solution xy here is 2k minus 1, comma 2k minus 2. Okay. So that is the solution that we'll use to generate solutions to back to our general Pell equation for this problem. Okay, so uh, all we need to do is just apply Brahmagupta's. First, let's start with a small solution, x comma y. If we have a small solution, then so what does Brahmagupta's tell us? A small solution xy to so let xy be solution to x squared minus k over k minus 1, y squared equals negative a over k minus 1. Given this small solution, what does Brahmagupta tell us? So xy would generate the solution. If you apply Brahmagupta's, you can look back at Brahmagupta's. Copying over was not quite handy, but this nonetheless will give you the solution. So x1 x. So all right, let's be clear on our terms here. So n in our Brahmagupta's is our coefficient k minus k over k minus 1. X2 in our Brahmagupta's is this x term of this solution. So x2 equals 2k minus 1, and y2 equals 2k minus 2. So putting this in, x comma y would generate the solution x1, x2, which is 2k. So okay, 2k minus 1 x plus x plus n y1 y2, so plus n times y2, which is 2k times y. That's our comma. The next would be x1 y2, so that would be 2k minus 2 x plus x2 y1, which is 2k minus 1 times y. So you can indeed see that whenever we have a small solution, x comma y, we'll get a larger solution by with this recursion. And the larger solution is going to be strictly larger. It's going to be positive. Okay, so good. So if you apply this enough times, eventually x will be greater than square root a. Definitely. Okay, so we've handled, so now we know that B is a subset of A. We know that whenever K has a small solution, K has a large solution. Now we have to do this in reverse. So what about the reverse? So should I new page? Yeah, let's do new page. Okay. So applying Brahmagupta's backwards, what we actually need now is a solution to, if we're given a large solution, so let's write this here, given large solution x comma y, let's aim to generate a small solution, smaller at least, x prime comma y prime. And let's do this here. So Brahmagupta tells us if you apply Brahmagupta on the smaller solution, then we have the going from the smaller solution to generate a larger solution would give us 2k minus 1 times x prime plus 2ky prime equals our larger solution, as well as 2k minus 2 times x prime plus 2k minus 1 y prime. Gonna check. Yep, equals, okay. And this is gonna equal our larger solution, which we'll just take x and y. Okay, so as I mentioned briefly here, if you solve backwards, you're always going to get an integer solution. So here we'll actually get a linear combination of x and y. And what is that going to equal? Okay, if we actually solve this, don't have the solution in front of me, but x prime plus Okay, gonna subtract the two equations. X prime plus y prime equals x minus y. So 2k minus 1 times that tells us 2k minus 1 x prime plus 2k minus 1 y prime equals 2k minus 1 x minus 2k minus 1 y. So subtract it from the first equation above. What do we get? Y prime equals x minus, just doing the calculations here, 2k minus 1 x minus 2k minus 1 y. Okay, so tells us that let's bring this up here. So y prime equals so that would be negative 2k minus 2, if I'm doing that right. Okay, I believe so. 2k minus 2 x plus 2k minus 1 y. Okay, seems good. Okay, and our x prime would be, what is x prime? X prime plus y prime equals x minus y. So it's x minus y minus that. Apparently it seems like it's 2k minus 1 times x minus 2k minus y. I'm gonna check this. Is it 2k minus 2 or x minus y? Oh, it's 2k. Okay, that makes sense. Minus 2k of y. Okay, so anyway, that was me solving a system of linear equations, and now you have the solution, x prime, y prime. Okay, so x prime and y prime are definitely integral. They're integers, but they're not necessarily positive, which is okay. You can take the absolute value of x prime and y prime, but then we also don't know if x prime and y prime are smaller. So that is something that we actually have to check. Pull up some calculations here. Oh, okay. All right, and so the idea here is basically, as we're taking a large solution xy, so xy are sufficiently large, and xy satisfy this equation here. So the ratio of x and y is going to be approximately square root k over k minus 1. The larger x and y become, the closer they become to that ratio. So if they're sufficiently close to that ratio, then it turns out that x prime and y prime are going to be positive. And I'm just gonna pull up the calculations here for the sake of time. Really, what remains here is just you just need to check that when x is greater than square root a, we'll have that x prime, the absolute value of x prime is going to be less than x. That's all you need to check. I'll see if I can pull up something. Yeah, okay. That is just straightforward computation because basically, here, the way you do that is basically because x squared is at least a, that tells you that y squared is at least something in terms of x squared. They're going to be sufficiently, so the ratio of x over y is going to be greater than your ratio of 2k over 2k minus 2k over 2k minus 1, basically. Yeah. I'll leave that to you guys. We definitely need to move on to another problem. definitely work out the calculations. It will be instructive on telling you how this infinite descent works at this at this terminal end. Okay, next problem here. This is from CAMO, which is a mock Olympiad. The one I participate in making. This is actually a problem made jointly by Sean and Eric, if I recall correctly. Anyway, so do there exist positive integers m and n such that n squared minus 1 over m squared minus n squared minus 1 is a positive integer? Same drill. Let's write this as n squared minus 1 over m squared minus n squared minus 1 equals a positive integer, okay? And you can just fix k, okay? So just show that for any k that you fix, you're never going to get a solution m comma n to this equation. Okay. Here's how we do that. Expand this out. So k times m squared minus n squared minus 1 equals n squared minus 1. So let's write this as k m squared minus k n squared minus n squared, so minus k plus 1, I believe, n squared equals, and what does the right hand side equal? K minus 1. Yeah, that's correct. Okay, same drill. Once again, we know we'll divide this out. M squared minus k plus 1 over k n squared equals k minus 1 over k. So once again, let's see if we can apply Brahmagupta's. The key to applying Brahmagupta's is to see if there is a nice solution to m squared minus k plus 1 over k n squared equals 1. So is there a solution to this? And if you do the same thing, that exact same thing that we did before on 2016 and 5, well, we'll see maybe k divides n. So we'll see, is there a solution to perhaps m squared minus k times k plus 1? N squared equals 1. Is there a solution? Well, sure, yeah, it's the exact same thing. So n equals 2 here, m equals 2k plus 1. So our proper solution to this actual Pell equation is m equals, I said 2k plus 1. Whoops. 2k plus 1, comma, 2k. 2k. Okay, that's our solution. So that means we can apply from Gupta's now. Gonna pull this up for reference. Oh boy. Okay. Let's just work it out. Okay, so here the idea is we want to apply infinite descent. And hopefully show that there is no, that infinite descent will fail us, basically. Because okay, so the factor, if you will, the thing we applied Brahmagupta's on, 2k plus 1 comma 2k, is pretty much the exact same thing that we had over here. This time over here it was 2k minus 1 comma 2k minus 2. So I won't bore you with the solving system of linear equations. I'll pull up the solution, see what it is, and see why infinite descent will fail in the small case. Let me find it really quick. So let's see. Okay, and it turns out, what is it? if we have a solution mn, then the smaller solution is given by m comma n gives here we go. Do we have it? Okay, no. Okay, I guess we'll derive it. We'll come in. So we have what we want is applying Brahmagupta's on here. So okay, so the system of equations is x1 times. So all right, so this is our value n. This is x1. This is x2. x1 times, so x times 2k plus 1 plus n times y2, which is 2k plus 2, 2k plus 2y equals our value m, and n would be x times y, so x times 2k, let's write it 2kx plus 2k, okay, y x2, okay, so that's 2k plus 1 times y equals n. So this system of equations, you'll get x and y in terms of m and n. What it is exactly, let's see. You get, okay, so x, yeah, same thing, okay, shouldn't be that bad. X plus y equals, if you subtract the two equations, x plus y equals n minus n. So that tells us y equals, does y equal n minus 2k times x plus y, and 2k plus 1 n. Mental math is hard. Okay, negative 2km plus 2k plus 1 n. I believe that's right. We'll see. What about x? X is equal to m minus n minus y. So m minus n minus y, 2k minus 2k plus, okay, yeah, 2k plus 1 m y, yeah, okay, minus 2k plus 2 y, n, sorry. Okay, that's our solution. And now infinite descent needs to fail at some small value, some small point. Why is that? So we need to see that, we need to show that there is no solution to our Pell equation. Want to show there's no solution to our Pell equation k x squared minus, okay, minus, whoops, yeah, kx squared minus k plus 1 y squared equals k minus 1. Why is that? Why is there no solution, small solution, xy to this equation? The reason here is if you take this, let's actually copy the other form. So here, x squared, k plus 1 over k, y squared equals k minus 1 over k. And what we'll also do is, let's expand this out. So we have x squared minus k times k plus 1 times y prime squared equals k times k minus 1. Yep. So why is there no small solution to this equation here? The reason is that if you take this solution modulo, let's take it modulo k. Oh, yep. Let's take it. Do we want to keep it that way? Okay, well, let's work with km squared, kx squared. Well, okay, let's write this back. Let's look at each of the three forms we have. So kx squared minus k plus 1 y squared equals k minus 1. If you take this solution, modulo k, well, then we see modulo k. This means this first term is just 0. The second term is negative y squared, is congruent to negative 1, modulo k. Okay, and so what that tells us is that y squared is congruent to 1 modulo k. So y equals 1. So one possibility for this would be y equals 1. Is y equal to 1 a solution? No, because k would equal 0. So no, that's not a solution. So this means that we'll need y to be at least there's no solution. There's no solution y less than root k. Okay, and what you'll note that this is quite basically a clone of our previous problem. Earlier, we wanted to show that there was no solution when x is less than root a. Over here, we're going to have there's no solution to y less than root k. Just apply Brahms-Gupta's in reverse. See that you can always generate a smaller solution when y is greater than root k until you reach y is less than root k, by which time you get a contradiction. Okay. Now, 1 hour apparently was still I overestimated how long 1 hour is. Problem 3 is our last problem, but we'll skip ahead to problem 3 because it's quite a bit more interesting. Problem 3 is we'll take the ideas of problem 1 and problem 2, but it's problem 1 and problem 2 on steroids. Quite a bit more complex. More steps to this. Okay, let's go ahead and just jump right in. Show that there is no solution to this equaling a perfect square. Okay, well, let's let the perfect square be c squared. Okay, so a squared plus okay, before I'm just gonna say what I'm gonna do is set up the Pell equation, tell you how to apply Brahms-Gupta's. The actual details of applying Brahms-Gupta's are I'll just run through them because I do have it by my side. But anyway, let the perfect square. Suppose the contrary. Suppose there's a solution A, B that gives this equaling a perfect square. So a squared plus the ceiling of 4a squared over b has to equal some perfect square c squared. Ceiling is a bit messy. We don't quite know how to deal with ceiling. But okay, what we can do is now we know ceiling of 4a squared over b equals c squared minus a squared. And this means that so this number here is slightly larger than 4a squared over b, but not large by that much of a margin. So to be precise, let's multiply b by both sides. So we have b times the ceiling, 4a squared over b equals b times c squared and minus a squared. And what this means is this is the number here, which is the smallest multiple b that is greater than or equal to 4a squared. So this here is equal to 4a squared plus k. This number here, b times the ceiling, is the smallest multiple b that's greater than or equal to 4a squared. So it can be written as in a form 4a squared plus k, where we know k is less than b. 0 is less than or equal to k is less than b. So now we have this is of the form 4a squared plus k equals b times c squared minus a squared. Rewrite this. It's a Pell equation in terms of c and a, where b is the coefficient. So the Pell, this is the Pell we get. B c squared, minus b plus 4 a squared equals k. Okay, so again, we aim to apply Brahma-Gupta's. See, if we can apply Brahma-Gupta's, and so that means we aim to solve the equation b. Well, that would be x squared minus b plus 4 over b y squared equals 1. Is there a solution to this? Well, let's see. So let's try this out. Let's assume b divides y. So take y to be b times y prime. So x squared minus b times b plus 4 y prime squared equals 1. Is there a solution to this? Yikes. Okay, so we've got a problem here. The reason being, the actual solution, the algebraic solution to this, if you were to one such solution actually is if you take y prime to be 1/2, then this actually completes a square. This would be y prime equals 1/2, and I don't know what does x equal. X equals something like b plus 1/2. Is that right? Yeah, b plus what is this? 2b plus 2b plus 1/2. Thinking. Okay, what is this? 1/4 times b squared plus 4b plus 1, so that is 1/4 b squared plus b plus 1. Okay, that is, yeah, 1/2 b plus 1. That is actually a solution, x and y. But if you try to apply Brahma-Gupta's on this set of x and y, it will be very problematic. The more times you apply Brahma-Gupta's, the larger your denominator will be. So the first time you apply Brahma-Gupta's, you'll get something over 2. Then if you apply a Brahma-Gupta's again, you're going to get something over 4, something over 8. That's not going to work. We are okay though if b is even. So note that if b is even, then we'll actually, oh, why did I erase this? 1/2 b plus 1, comma 1/2. So we're good. We're good if b is even. Then good. Because then your actual value of y would be b over 2, your value of x would be b over 2 plus 1, and they're both integers, and we're okay. So that takes care of the b is even case. What you'll end up doing is something quite analogous, almost exactly the same thing as problem 1 and problem 2. So I won't run through any of the details there. But just solving b is even is not good enough here. Okay, we actually need to try something stronger. So again, let's go back to our x squared minus b times b plus 4, y prime squared equals 1. So now we actually want to find some actual integer solutions in general too, in terms of b. See if we can actually get something, get a general, get a solution set x comma y prime in terms of b. If you actually, so first of all, this is a proper Pell equation. The right-hand side is equal to 1. So you know that for any value of b, you're going to have a solution x, y prime. So if you test out small values of b prime at b and look for small solutions x comma y prime, then with enough effort, that is quite a tedious task, but you'll discover that one such solution is the following. Gonna be quite a monster. So I can write this down here. A solution is what do we have this here? Okay, here's our solution. B cubed over 2 plus 3b squared plus 9b over 2 plus 1, comma 1/2 b squared plus 2b plus 3 over 2. So yeah, both of these numbers are always integers. And yeah, what a monster. They're not easy to find. Although I think if you take the b as even case, then what actually happens is that these two solutions are just what you get when you take this solution and you apply Brahmagupta's and generate it one more time. So you can actually derive this solution by taking this and generating it once more, hoping that it applies not just to b as even, but also to b as odd. Anyway, but here's the solution that you'll need to apply Brahmagupta's, and you can now apply infinite descent. Now, if you apply infinite descent, I'll tell you what you'll get. You for your value c comma a, you can always decrease it until a is less than square root, until what? Until a is less than or greater than? Yeah, less than b to the 3/2. Okay, so once a is less than b to the 3/2, this won't decrease anymore. So now we just need to solve our equation, a squared back to what we had before. A squared plus the ceiling of 4a squared over b is a perfect square where b is at least a to the 2/3. Now I notice we're quite out of time. This right here actually has nothing to do with Pell equation. The rest is just the bounding work. In the case that b is greater than a, then this actually becomes quite clear. There's no solution. In this case, you'll need to do a bit more work, do a bit more algebra, but you'll see that there is no solution to this. The rest of this problem is just working with floors and ceilings, and that's all for the Pell equation part of this problem. If you're interested in seeing full solutions to each of these 3 problems, you can actually find these online, and you'll find the full solutions to them. But yeah, to conclude, notice how we had one technique applied very similarly to 3 problems, even though the 3 problems do look quite nothing like each other. Okay, hope you enjoyed this. Thank you very much. My time's up.